that has somewhat stuck, as you can see on the title slide. After her PhD, she did a postdoc and then became a research scientist at Caltech, and finally returned to MIT in 2002 on a faculty position. Since her Caltech days, she has been involved with LIGO. She was also part of the very famous and groundbreaking discoveries that came about since 2015. And I guess we'll hear a little bit of that as well. I don't want to get lost in all the many merits she has collected. Let me just say that she's one of the few true experts in two apparently disparate fields, gravitational wave astronomy and quantum measurement. And we're very happy that you're here. We're very much looking forward to your talk.
Thank you, Eva. Thanks very much for having me. It's a pleasure to be here. Now I have to make a couple of disclaimers. The first one is that I'm going to show you a bunch of data from the LIGO instruments, and that is the work of literally hundreds of scientists. So I'm the messenger here. And then the other thing I wanted to say is that this is a disclaimer I make because I'm here at the Quantum Optics Institute. There will be quantum optics in my talk, so don't lose hope. But I will also tell you a little bit about the astrophysics. So I'm going to sort of mix and match these two ideas. So what I'm really going to do here is I'm going to tell you about sort of the new window to the universe that gravitational wave detectors are opening. And so many of you are familiar with the first discovery. Some of you might have been quite young when that happened. It's almost 10 years now, a couple of months short of that. So I'm going to walk you through the story of discovery and to the technologies that are driving the field forward. That's really the goal of the talk. So just to orient you both into what gravitational waves are and to orient you to the history. So gravitational waves were predicted by Einstein as part of his general theory of relativity in 1916. The gravitational waves were the dynamic part of his relativity theory. And in his early papers in 1916, he was very pessimistic about them. He actually concluded the paper by saying gravitational waves would never be useful for anything. Now that kind of remained the case until at the time they were just the wave part of general relativity was really out of reach. Einstein himself even questioned their very existence in the 1930s. He went quiet on the subject after he wrote a paper where he claimed gravitational waves didn't exist, but then he retracted the paper after the referees showed that he was wrong. So, he was very ambivalent about gravitational waves. He thought there might be some kind of sort of mathematical oddity of the theory, not necessarily real. And he was justified in his opinion because when you think about gravitational waves from ordinary stars like our sun, which was all that was known at the time, they're really, really faint. But then came in the 1960s and 70s discoveries of neutron stars and black holes. And these are now objects that have a lot of mass in a small volume. So they're gravitationally quite extreme objects. And when you then ask, what would be the gravitational radiation from such objects, it starts being a little bit more tractable. And so the next hero of our long story is Kip Thorne, who in the late 1960s and 70s, new professor at Caltech, took these discoveries of neutron stars and black holes and was among the pioneers to tell us that we can calculate the amplitude of these gravitational waves from this rather nonlinear general relativity theory. And he put the amplitude at about 10 to the minus 21 for a pair of neutron stars or lightish black holes that are in a galaxy close to our own. And then about the same time, this man, Ray Weiss, was also a young professor at MIT, started to think about the problem of how one might detect gravitational waves. And to detect gravitational waves, the one property of theirs that you need to know about is that as they propagate through space, they shrink and stretch the space-time itself. And so Weiss was not the first to propose one might use an interferometer to detect them. But then what he did was he laid out that these interferometers needed to be 4 kilometers long, or of order kilometers, and he laid out the technologies for how one might build them. And I'll just say as a historical note that I'll come back to later here, the Max Planck Institute in Garching also played a very big role in the early years of these gravitational wave detectors. I'll come back to that. And so that's how the field got started. Weiss and Thorne met in 1975, quite by accident, and they hatched up the concept of LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And LIGO is exactly this Michelson interferometer, and initially designed to achieve a displacement sensitivity of 10 to the minus 18 meters. And if you scale the gravitational wave amplitude, which scales by the length of the instrument, an instrument like that would be capable of measuring gravitational wave strain at the level of 10 to the minus 21, which Thorne had predicted would be the sort of a target number. Now, these observatories came into being in the late 1990s and early 2000s, 4-kilometer long detectors of LIGO in northwestern United States, about a 3-hour drive east of Seattle, and in southeastern United States, about an hour outside of New Orleans. And there are two important things that you have to do to build a gravitational wave detector. And that is going to be sort of my introduction also to tell you that these gravitational wave detectors are essentially giant optomechanical instruments. Okay, so the two things you need to do is you need to make mirrors that are very, very still at the level of 10 to the minus 18 meters, so that their displacements are dominated by the passing gravitational waves. And to do that, the two technologies that we use at a very high level is, first of all, we use a vibration isolation system that works very much like noise canceling headphones. We measure the motion of the platform, and then we have feedback loops to correct for that motion. And that process gets us to about 10 to the minus 13 meters. So let me just say, if we just left a mirror of LIGO, for example, just sitting in an ordinary space, not too noisy, not too quiet, it would move at about a micron. So this first layer of isolation gets you those first 7 orders of magnitude. And then we take the mirrors of LIGO, which are 40 kilograms and about 35 centimeters in diameter, and we hang them from 4 stages of pendulum. And the pendulum, each stage of pendulum acts as a mechanical filter, and then that gets us down to 10 to the minus 18 meters. Okay, so that's the first thing. You get your mirrors to be shielded from all external forces to the degree that you can. And now you have the next factor of 1 trillion, which is that you need to measure these really small displacements, and we do that using the laser light. That's the L in LIGO. And that we do, we use 1 micron laser. That's the narrowest line with high power lasers that we know how to make at the time. And there we're trying, so the challenge we're up against is we are trying to make a measurement that's a factor of 1 trillion smaller than the spacing of the tick marks on our ruler, which is the wavelength of the laser light. And we do that by averaging over very large numbers of photons. We use very high-powered lasers. The ultimate target for LIGO are 200-watt lasers of CW power. And then we also use Fabry-Perot cavities in the arms of LIGO to amplify the phase sensitivity of the signal. And when we do all of those things, we can put together for ourselves a gravitational wave detector that's capable of measuring 10 to the minus 18 and now 10 to the minus 19 meters RMS. Okay, this whole enterprise has been funded by the National Science Foundation in the US for the last 40 years. And this man, Barry Barish, is credited with the scientist who led to the construction of the observatories from, Now, LIGO is part of a global network of detectors that you might find fun to look at. So there is the 2 in the United States. There's Virgo, which is a 3-kilometer long detector in Italy. There's Geo 600, which is a 600-meter long detector here in Germany, outside of Hanover. And then there's a 3-kilometer long detector, Kagra in Japan, and a 4-kilometer long replica of a LIGO detector in India. And then for decades now, there has been plans for LISA, which is a space-based detector. Okay, so that's the global network of detectors. Now, we fast forward to, from the time of Thorne and Weiss meeting in 75 to the building of the LIGO observatories in the late 1990s to early 2000s to this as the first detection. All gravitational wave observations are numbered by their date of observation. So you can see this was in 2015, September 14th. Okay, so we're coming up onto the 10-year anniversary of the first detection. And what you see is these are the space-time wiggles. And one of the things that I'd like to point out to you is the signal lasts about 200 milliseconds in our detector. At the moment that this is from two colliding black holes. From the moment that so the signal is made up, I should just say, these black holes or neutron stars, whatever the binary system is you're observing, is losing energy to gravitational waves. And that energy comes out of the orbit. And that's why these things come spiraling closer and closer together and collide. And at the moment of the collision, somehow I'm supposed to get this to work, but it doesn't matter. At the moment of the collision, which is the maximum of the signal, notice that the strain was 10 to the minus 21. So big check mark for Thorne. He told us that in the late 1960s. And if you ask how much were the mirrors of LIGO moving at the time, it was 4 times 10 to the minus 18 meters. It's a big check mark for Weiss. He taught us how to build these back then. And from the structure of this waveform, we could tell that the two black holes were about 30 solar masses. At the time that they plunge into each other, they were moving at about half the speed of light. And that's something everyone should just take a pause on. You take something that's 30 times the mass of our sun, and it's moving at half the speed of light. So these are extreme environments in the cosmos. They were located about 1.3 billion light years away, and they lost about 3 times the mass of our sun to gravitational radiation during the merger. Okay, so that won the 3 founding fathers a Nobel Prize in Physics in 2017. And that's really the preamble to my story. I want to tell you what's been going on since then, because most of you know this part, and maybe the younger people haven't seen it. But so really what's happened since is pretty exciting. And so let me tell you about the GW 170817. So this was in August 2017. And that was the first time that these observatories saw a collision of 2 neutron stars. And neutron stars are kind of are the lighter cousins of black holes. The mechanism for formation is thought to be similar, which is that you take stars, usually stars like our own sun or a little bit heavier. And when they run out of nuclear fuel, the radiation pressure that keeps the star up buoyant against its own gravity shuts off because the nuclear engine is shut off, and the star collapses. And which is a supernova. Now, if the star is about 1 to 2 times the mass of our sun, it will collapse to a neutron star. If it's a bit heavier, 3 to 5 times the mass of our sun, it will collapse to a black hole. So this was the collision of 2 neutron stars, and we could tell right away because look at the time scale. So black holes, the time scale I showed you was about 200 milliseconds. This thing goes on for over a minute in our band. And so we knew already this was a much lighter object. And then 1.7 seconds later, there was a signal that showed up in a gamma ray telescope, in the Fermi gamma ray telescope. And this sort of set the astronomy world abuzz. These were detected. Now you can triangulate the signal from the 2 LIGO detectors and Virgo, and you could tell that it was in a patch of sky in the southern hemisphere. And astronomers it was daytime at the time this was detected, and astronomers had about 11 hours to prepare their telescopes in the southern hemisphere to go look for this object. Now, what should they look for? If the theories were correct, this is called a kilonova, and what it would be is a pair of neutron stars that has spent billion years orbiting each other and giving off nothing but gravitational waves. But at the moment of the collision, it's smashing 2 nuclei, and you should have a very spectacular light show. So all these telescopes lined up, and then what ensued was astronomer's night to remember. It's a very busy plot, but I want to point you just down to, first thing to look at is on the left, you see gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, radio, and in every band of electromagnetic radiation at different times after the first gravitational wave was detected, something was seen. And I'll point you in particular to, the pointer isn't doing his job, I'll just point. So I'll point you to this, this plot right here. This is telescope DLT-40. And now every one of these telescopes you look at, in the crosshairs, it sees it's pointing to an object, right? And then, so that was what was seen that night. And then when you go back 20 days earlier, there's nothing in the crosshairs. This is an object that lit up in the sky, and this is believed to then be the first observation of two neutron stars colliding, and you're seeing the light show that ensued. And that light show, by the way, continued not just, well, the optical glow continues just for hours, but in the radio, it goes for weeks and months, okay? So this has been followed now for a long time. And the thing that was very exciting about that, I'll skip was you can measure the spectra of the optical emission. And you can see as days go by and you measure the spectra, this was the spectra of watching heavy elements being formed. So let me just say why this was so exciting. It has long been a mystery here on the Earth that we have too much gold and platinum in the heavy elements. And you might kind of think of that as an absurd statement, because as we know, entire civilizations have been won and lost over gold because it was seen as precious and rare. But astrophysically speaking, all of the elements that we are made up of here on the Earth should come from our star, the sun. Now, it turns out the sun has neither enough neutrons nor the correct energetics to provide all the elements of our periodic table. And in fact, stars like our own sun fuse elements up to about iron 56, and then they can't do much more. So then the next place you look to is supernovae. That's the other place where you should be able to form heavier elements. And if you look at what supernovae can do, you again have an enormous lack of abundance. You cannot explain the gold, platinum, the lanthanide, and the actinide series. We just haven't known where those come from. And so it has been hypothesized that those then must come from neutron star collisions. And in fact, these spectra showed that. In fact, we saw something on the order of 50 Earth masses of gold being created in that collision. And so that was the first time that we were able to sort of solve the mystery of where do the elements here on the Earth come from. And for me, sort of as part lab rat, instrument builder, and part dreamer of the universe, that's amazing, because what it says is that in the vicinity of our solar system, sometime in the past, neutron stars must have collided, because we have these elements here. They didn't come from our sun. Okay, so it tells us a little bit about our own history as well. So this was there was a number of very interesting discoveries that came from this. I won't talk about them. I already talked about gold. We learned a little bit about the Hubble constant and the history of the universe, but that was one of the things. And the thing I want to talk to you about now is, okay, we're going to shut off most of astrophysics, and now we're going to move to the instrument. And I've got the claim I made at the beginning of my talk was we're opening a new window into the universe. And one or two detections does not a window open. That's just a little crack, right? So I'm going to tell you about what we're doing. So in the time since those early detections, we've observed more than 300 astrophysical events. I'm not going to go through even the small fraction of them, other than to say that the LIGO has operated in a series of observing runs. In the first observing run, which was where the first detection was made, we saw that first detection and two other events. In the second observing run, we saw something like 8 events. In the third observing run, we've seen over 50 and so on. So the list keeps going. And what are we doing to get to that place? So what we're doing, we've almost nearly 300 sources are detected. There are many, many astrophysical mysteries that are being uncovered, and they remain mysteries. We're still trying to uncover them. I'll talk about just one or two. I promise I would be done with astrophysics, but these are too interesting not to say something about. Because in the end, if you just collect 300 sources, that's stamp collecting. What we really want to do is we want to understand something about the universe. So one of the things, and some of you might have I've mislabeled this. This thing that says GW 190521 is actually GW 231123. It is the heaviest black hole system that we've detected until now. And I don't know if you saw it, it's been in the news. It just came out last week. Okay, so it was detected in 2023, but we finished the analyses. Now, why is it so interesting? It's so interesting because it's the first time that we see black holes that are 100 times the mass of our sun collide together and make black holes that are 200 times the mass of our sun. Now, this remains a mystery because there is something in astronomy called the upper mass gap. And what it is that normally by the process I described, where stars go supernova and collapse into a black hole, if the star is much heavier than about 50 solar masses, it cannot collapse to a black hole. It just explodes. It doesn't collapse. And the reason is because of pair production. So you have these, electrons and positrons forming pairs, and therefore there's no more radiation, and so the star collapses on itself and goes into a shock and explodes. So you do not, from the physics of these systems, expect black holes that are about more than 50 or 60 solar masses, and here we see them. Okay, and that's a mystery. So what else could they be? What they would be then is two heavy black holes that have found each other and are orbiting and collapse. So they've gone through this process many, many times of accumulating mass by merging with another black hole. That creates another mystery, which is where in the universe can you find enough density of black holes that they would find each other and do this process repeatedly in the age of the universe? We don't know. Okay, so I just wanted to point out that there are these kinds of mysterious things that we don't know about, that these instruments are now starting to shed light on. Okay, but I'm going to shift now and tell you about how these instruments work and how is it that we're getting from the first ones to these 300 detections. So on the left side, you see it's a plot. This is a spectrum of the strain noise in LIGO, and on the horizontal axis is frequency. And the frequency is the frequency of the gravitational wave we'd like to measure. And LIGO has been built up in a series of successively improved detectors. The first curve, the green curve, was initial LIGO, which ran from 2000 to 2010. The red curves are advanced LIGO during observing run 1, and that was the sensitivity that these detectors had when those first detections were made. The blue curve is what we have been designing towards since the early 2000s, and then the cyan curve is something we call upgrades, and I'll tell you what those upgrades are and how we've gotten there. And what you see then is also that, in observing run 1 and 2, we had a pretty slow rate of detections, about 1 a month. And then in observing run 3, that went up to about 1 a week. And now we are in a state where we see almost 1 a day, 1 every 2 days. Okay, and these increase in the observation rate comes with increases in detector sensitivity. So let me tell you a little bit about what limits the detector sensitivity and what can we do about this. So this is the sensitivity of advanced LIGO. The black curve is the target sensitivity that we designed to in about 2000, 2002. And what it's made up of is all these other colored curves. And the only two that I'll point your attention to are the magenta curve, which is quantum noise, and then the red curve, which is the Brownian motion, the thermal noise of the optical coatings of the LIGO mirrors. Now, anytime you do an optomechanical experiment, as LIGO is, you're coupling optics to mechanical motion, you will contend with the thermally driven motion of the oscillator, and you'll contend with the quantization of the light. And those are the two light sources right there. So in LIGO, at the high frequency end of the quantum noise, is shot noise. It's really just our ability to count more photons. And if you want to do better there, you would increase your laser power and you would make a stronger measurement. And as was already introduced by Lucas a little bit earlier, you pay a price. Remember, these mirrors are movable. And as you increase your laser power, the amplitude fluctuations of the laser light are going to kick the mirror, and that gives you a back action. Okay, so that's the measurement conundrum. Now, these two noise sources were predicted already in the 1980s, but let me say what we're doing about them. So let me start with a prediction from Carl Caves. This is a 1981 paper, and the thing I want to draw your attention to was few things. He says this is caves. I don't know if you are used to reading his papers. He writes the best abstracts because the whole paper is laid out in the abstract. He says, look, there are these two fundamental noise sources. There's photon counting error, and then there's radiation pressure error. And because the power is low enough right now in the lasers, we don't have to worry about the radiation pressure. We just worry about photon counting. If you want to do something about it, you must inject a squeeze state of light in the normally unused input port of the vacuum, with the squeezed vacuum. So how does that look? Here is an interferometer. We set up the arms of the interferometer such that the two arms are the path lengths are such so that we have complete destructive interference here at the output. All the noise on the laser, therefore, goes back towards the laser. And because we have this open port, this unused open port, vacuum fluctuations enter the interferometer. And here I've depicted them in phase space as we normally do in quantum optics. And this again needs no further explanation. Here is a vacuum state. And because of the symmetry of the beam splitter, just for the same reason that all the laser light goes back to the laser, all of any field coming in through the output port will go back to the output port, except that it will superpose with some coherent light that comes out because of path length imbalance that might happen due to a gravitational wave. And this superposition of your coherent light with the vacuum state gives you the shot noise as Caves told us. Now, the same vacuum fluctuations when they enter the interferometer and superpose with the very intense fields at the mirror give us the fluctuating radiation pressure force, and that's the thing we call the quantum radiation pressure noise. Okay, so what can we do about this? Caves told us that also in that 1981 paper. He says, well, instead of a vacuum state, inject a squeeze state of light, and then make sure your squeeze state of light is oriented such that your squeezing ellipse, its narrowest part, overlaps with your signal, and then you'll do better. Your signal to noise will improve. And indeed, that then is the experiment we did. So now fast forward to 2019. This has been decades a decade in the making. On the left side is a very busy plot, but I don't want to belabor it too much other than to say in the green box is a LIGO interferometer. A laser seeds it. And then at the output in the far upper right is where we would normally detect the gravitational wave signal. And the thing that we've done now is we've put in this yellow box and that OPO, and we're creating a squeezed vacuum states that we inject into the interferometer. And the interesting thing to look at then is the curves on the right. The black curve shows us what the performance of the advanced LIGO detector was with no squeezing. And then the green curve is the same with this squeezed vacuum state injected. And we see an improvement of about 3 dB from that. Now, that was all very nice. And that was, you remember I told you we had this dramatic change in the detection rate. So that was when we went to about 5 detections per month when we added this, compared to the 1 per month that we had in observing runs 1 and 2. So this was what we did in observing run 3. This was one of 2 or 3 improvements, but this was the lion's share of the improvement in detection rate. Okay, now if you zoom in very carefully at the spectrum, what you will see is that in this region, on the low frequency end, you are actually making your noise worse. Okay, so now the red curves again, your squeeze curve, and indeed at high frequencies, you're seeing the benefits of squeezing. And so, of course, this is also something that Caves predicted. What we're seeing here is we are now sensitive in the amplitude fluctuations to this long part of your squeezing ellipse. And so now this is the back action. So what could we do about that? Again, let me just say, I've told you Caves writes fantastic abstracts. So here's a great one. There has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. Okay, wouldn't we all love to write an abstract like this? And it turns out, so here we are, almost 40 years later, and we saw those radiation pressure fluctuations. Let me just say that was not unexpected. There have been many tabletop experiments in anticipation of this, and some in my own group and some in many other groups, including optomechanics groups that have seen this radiation back action. But this was finally, they were here in LIGO. Okay, So what can we do about that? So now let me come to another very important and seminal paper. So right around 2000, we were starting to design advanced LIGO. When this paper came out, Jeff Kimball, Yuri Levin, Andrei Matsko, Kip Thorne, and Sergei Vyachinin, and they showed us that, in fact, advanced LIGO would be stuck with this quantum noise. What do you do? How do you get around this? You know, it's fundamental. This is the quantum fluctuations of the laser light. And they showed us that one could do three things. So it's a busy plot, but I'll show you what they are. So you can ignore variational and squeeze variational readouts because those don't turn out to be useful. But it is quite useful to look at the curve they call conventional. That is a curve if you had no squeezing. So they said, look, you can do the following. Inject squeeze light at some fixed squeezing angle, and that will give you the dashed curve. Okay, so what is that? That simply says you have a squeezing ellipse, and at every frequency of your measurement, your squeezing ellipse is a fixed orientation. And that's, in fact, a reasonable thing to do, because when we make a squeezer, that's what a squeezer does. It gives you a particular squeezing ellipse, and at every quadrature, it's a fixed quadrature at every frequency. But then they said, look, if you could make something where you could actually make your squeezing ellipse rotate as a function of frequency, then you could get this curve here, which is the squeezed input curve. And we love that because that, in fact, is what a gravitational wave detector needs to be. It needs to be broadband because we don't know at what frequencies our sources come. And then they showed one other thing, which is called this HSQL. SQL is the standard quantum limit. Now, many of you in the quantum optics field deal with SQLs, and in fact, in quantum measurement. One of the things I have learned is that standard quantum limits are neither standard, every field defines their own, nor are they a limit, because as you can see, you can go below it. Okay, so what is one? In this case, it's asking a very fundamental question. It says, if I use light to measure the position of a particle, how well can I do? Right, and the answer is, well, of course, I want to increase my light power, because then my imprecision noise will go down, my shot noise will go down. But then, of course, the radiation pressure fluctuations will disturb my measurement more, and that's the tension. And the standard quantum limit is simply saying at every laser power, what will be that balance? Okay, and they showed that you could indeed go below this standard quantum limit by using quantum light, in this case, squeeze light. And what it's really relying on is quantum correlations to get around the standard quantum limit. Okay, so let me just say a little bit about how these curves come about. And to do that, I'll introduce briefly optomechanical squeezing. So optomechanical squeezing is a process by which, when light couples to a mechanical oscillator, it can become squeezed. And the way you can think about that is that you have a system, just as Lucas introduced a few minutes ago, but it's an optical cavity where one of the mirrors is movable. Now, if you pump this cavity with a coherent state, you have both amplitude and phase fluctuations on your light, just minimum uncertainty. And the amplitude fluctuations will apply a fluctuating force to the movable mirror. That fluctuating force will displace the movable mirror. The displacement of the movable mirror will in turn imprint a phase shift on the light, and that correlates the amplitude and phase fluctuations. That's a heuristic picture, but it's a very useful way to think about this. And that is called optomechanical squeezing. And what that does then is you can create this kind of squeeze state of light. And pictorially, what that does is you start off with some vacuum state, and you can create a squeeze state. And then depending on the dynamics of the system, controls how much squeezing you get and what the orientation of your squeezing ellipse will be. Okay, so we've done experiments. We and other groups have done experiments also to show that this effect works. So this was an experiment we did on a tabletop with a micro mechanical oscillator. So it's a mirror that's about 100 nanograms in mass, about 100 microns across. That's suspended as a cantilever. And then you can see from this plot that the flat line at 0 dB is shot noise. And then anywhere where the spectrum goes below shot noise, that's squeezing. And everywhere above it is the long part of the ellipse, the anti-squeezing. So we know optomechanical squeezing exists. We know it can even be useful. People have thought about how to use these as squeeze vacuum sources. But what I want to go to is that we then were able to go into the LIGO detectors and make the measurement. So this was a measurement that was done in 2020. So shortly after we put in the frequency, fixed frequency squeezing, and you can see that that was the curve that the KLMTV paper had shown us what would be possible. And then here we were able to make that measurement with the advanced LIGO detectors. And then if you look at the dashed line, the dark dashed line, that's the standard quantum limit. And we were able to achieve about 3 dB below the standard quantum limit. And all we've done in this case is two things. We've injected squeeze light, and then that optomechanical coupling takes our squeeze state and shears and rotates it as a function of frequency. And that's what you see over there. We start off with just a vacuum state, but if you start off with a squeeze state, then the optomechanical interaction changes the noise properties, the properties of the noise phase space in the interferometer. Now, this is great. It has two caveats that I should tell you about. The one is that to make this measurement, we had to first subtract out classical noise. So LIGO at the time was not operating with low enough noise. It had classical noise that was masking the quantum noise in this regime. So if the classical noise had been low enough, then we would have seen this as an operational thing. But in this case, we had to subtract it out. The second thing I'll say is no one likes to run an instrument at this because it presupposes we have signals, gravitational wave signals at 40 hertz. So you don't want to do that. All right, so then KLMTV told us what to do next. Remember, they told us you can make a broadband instrument. So here's a nice way to think about this. This is the blue curve is advanced LIGO with no squeezing. The red curve is advanced LIGO with squeezing, where we have oriented the squeezing ellipse so that we get all of the improvement we can at higher frequencies. Now, what that says is that we've oriented our squeezing ellipse so that it gives us maximum improvement at the highest frequencies. At low frequencies, then we would like to have the squeezing ellipse be orthogonal to the one at high frequencies, because that's a change in quadratures from phase to amplitude. And at all intermediate frequencies, we would like something in between. So what we would love is to have an instrument that can take a squeezing ellipse and then as a function of frequency continuously rotate that squeezing ellipse. Now, why? And if you could do that, you could get this. Now, why does the interferometer do this? What is magical about that 100 hertz? Okay, what's magical about that 100 hertz is that LIGO has 4-kilometer long Fabry-Perot cavities. That's the storage time. That's the line width of those cavities. So it is the optical cavities that are creating this rotation and making the red curve, making it a pain for us. So if there was a way we could undo what the interferometer was doing, we could get the black curve. And KLMTV told us how to do it, which is to reflect your squeeze state off of an optical cavity. Now, remember, an optical cavity is a resonator. Its amplitude response is a Lorentzian, but it also has a phase response, which means within the line width of the resonance, it gives you a phase shift. It rotates your squeezing ellipse. The conundrum here is we needed another 4-kilometer long cavity to undo what the actual cavities of the interferometer were doing. Now, no one wanted to build a 4-kilometer long cavity. So instead, we built a higher finesse 300-meter cavity. And now LIGO has a new appendage. There's a 300-meter cavity that's running alongside the 4-kilometer cavity. And we use that cavity to reflect the squeeze light off of, and it gives us this continuous rotation. And then we have broadband improvement. So you see the black curve is without squeezing. The green curve is what you get with this fixed frequency squeezing that we were doing in 2020. And then the magenta curve is what we get now, reflecting that squeeze light off of the 300-meter long cavity. And you can see we dramatically can undo the the back action price we were paying from the squeezing. And that is the state in which LIGO runs now. It's a broadband instrument. And then one could do the same experiment we did with the frequency independent squeezing, which is to ask, well, how close to the SQL can we get? So we did the same experiment. Now remember, KLMT, we would predict the curve that says squeeze input and is shaded in magenta and busy plot, but I just want to draw your attention to, indeed, we can realize that. So now we can realize broadband improvement and operation below the standard quantum limit. And the key thing here, that's kind of amazing to really think about what's happening here. On the one hand, we're injecting squeeze vacuum states, which we make with nonlinear optical systems, and that's fine. But what's really happening here then is that the coupling, the quantum correlations of the light and the mirrors in the interferometer, the ponderomotive squeezing, the optomechanical squeezing, is then giving us this added advantage. Okay, so we're basically able to operate 3 dB below the standard quantum limit due to this frequency-dependent injected squeezing and the optomechanical squeezing that's in the interferometer, which is the light mirror correlations for a 40-kilogram mirror. Okay, so let me just end by a quick look at why we are where we are and where we're going next. So we, so I told you already that Caves in the early 1980s gave us this idea of using squeeze states of light to decrease the photon counting noise initially, because there was no plans for us to ever see radiation pressure. Lasers were not powerful enough then. Then in the mid-1980s, Slusher et al. Were the first to observe these squeeze states of the electromagnetic field that were at the time detected by non-degenerate full-wave mixing in sodium atoms. A couple of years later, Kimball and colleagues injected the squeeze light into a toy tabletop interferometer and showed you actually can make an improvement in the displacement sensitivity of the interferometer. And then all of that work was forgotten because we were busy doing an initial LIGO and there was no need for anything further. Now here comes the LIGO 2. So by the way, advanced LIGO in the early days of its conceptualization was called LIGO 2. It didn't have a name yet. And so this was in 1999, and this is a quote from that original project book. Project books are things that go to funding agencies for big experiments with lots of dollars attached. The recommended program is tightly focused around a reference design for LIGO 2, which is planned to be a quantum limited interferometer with very significant increase. And right around that time, we understood that quantum limited means we're at the end of the road unless we become clever. And then KLMTV gave us some paths out to becoming clever. Then there was a period of in 2002, a group of scientists, I was among them, but I'll point out David McClellan and Pinkoy Lam at the Australian National University, Roman Schnabel, who was at the time at Hanover, now in Hamburg, and my group, we got together and we set ourselves a challenge. We said, we want to make squeeze light. We want to make 10 dB at 10 hertz, because that's our operational band, in 10 years. And then there was a series of breakthroughs that led us to where we are today. We got to 10 hertz in 2004. We got to 10 dB in 2006, and we got to interferometer, injecting into interferometers in 2008, and so on. So, and that's how we got here. And so I'll just conclude by saying, we have a number of improvements coming up to advanced LIGO. As you can see, we just keep marching these curves down. And the thing that I want to point out is that in every situation, these quantum technologies are part of it. And the challenge we have now, which you all know from your own experiments, quantum states are very fragile. And so we're really just pushing hard on lowering optical losses and getting to more efficient readouts. There is a plan for third generation detectors, and those are these, there's a whole series of plots. Let me just tell you what they are. So this is advanced LIGO during observing run 3, advanced LIGO design, and an upgrade called A+. And you come to this family of detectors. These are third generation detectors that are planned to be about tens of kilometers. So in the case of the European detector Einstein telescope, it's a 10-kilometer design concept. In the case of the US detector Cosmic Explorer, it's It's a 40-kilometer design concept. And I'll just say one thing that's super exciting about them. And so if you get to these third-generation detectors, the prediction is that you can measure binary black holes out to a redshift of 10. Now, for astronomers, that is super exciting because we believe this redshift of 10 is when the first stars lit up. So if you can do that, you are going to measure every stellar mass black hole that ever collided. Okay, who gets to say that in a third generation of instrument, right? That's amazing. So let me then just say, these gravitational wave detectors are these exquisite quantum sensors. These quantum technologies are already deployed, and as these networks come online, every one of these future detectors includes these quantum technologies, and they're going to be capable of astrophysics that I haven't had time to cover, but they're also history making. I said, within a couple of decades of the first discoveries, if we get to these third generation instruments, we will be able to map out all the binary black holes in the observable universe. That's pretty cool. But I was also given some pause. I went to the Deutsches Museum yesterday, and I saw this there. And I understood another remarkable thing, which is that within a decade of these first discoveries, these detectors are also, making history in museums and textbooks. And that, I think, is another thing that really gave me pause, like, wow, that's unusual. And so let me just end with, we have this new window into the universe. Yes, we've seen black holes and neutron stars. Yes, we've confirmed Einstein's theory of general relativity. These machines work with exquisite precision. None of this will be remembered 100 years from now. What will be remembered 100 years from now is that we changed how we look at the universe, that we can see the dark universe without light, but with gravity, and also with light, as you saw from the neutron star case. This is the cast of characters that was involved in the quantum work. And as I've told you, LIGO itself is much, much more extensive than that, but these are the many students and postdocs in our quantum group here. With acknowledgement to the National Science Foundation, I just want to leave you with this thought that this is what a new window into the universe looks like. This is what we are seeing today, and it looks like it's going to be brilliantly warped and dark. Thank you.
Wonderful. Thank you very much. Now, questions for real. Who wants to go first?
Yeah, thanks for the amazing talk. I was wondering, could you comment on the role of the power recycling cavity for, this frequency dependent squeezing? Because you made this intuitive argument with the 4-kilometer arm, but as far as I understand, the LIGO detector is much more complicated with this.
It is much more complicated. So let me just say, for those who don't know, so, you have Fabry-Perot cavities in the arms of the L-shaped interferometer, but you also have cavities, a mirror, a partially reflected mirror between the laser and the interferometer. So you can think of this Michelson interferometer and this input power recycling mirror as its own Fabry-Perot cavity. And it's a technique for increasing the power that's going into the interferometer. So it increases the stored power. And it turns out, even one more complication, there's also a signal recycling mirror, which is a mirror at the output between the output and the beam splitter. And all of those cavities do two things. What cavities really do in these instruments is they increase the phase sensitivity because the light bounces multiple times and light builds up, right? And in each case, in the case of the power recycling, which is the input cavity, it is increasing the effective power at the input of the beam splitter. And in the case of the output mirror, it is basically taking your signal photons and letting them sample the path length multiple times. And so these are all, now what it does to the output of the gravitational wave detector is mostly it just lowers that sensitivity curve.
So there is no special, physics-related concept, which you need to take into account for this frequency-dependent squeezing, which you
yes. So there could be. So yes, so there is. So the output cavity plays a role, and the properties of the output cavity are important for us in designing the frequency-dependent cavity as well, because you're going to sample some of the phase shift from that output cavity as well. So yes, you do have to account for that. Yeah.
Yeah, thanks for the great talk. I was asking myself, when you are showing the strain versus frequency curves, you always have these peaks.
Yeah.
And they seem to be amplified when you are using squeezed light. What is the reason for that? Could you comment on that?
Yeah. So let me just say what those are. So in almost every instance, there are lines that we know and expect. So the first ones are very easy to understand. This is 60 hertz, 120 hertz, 180 hertz. These are power lines, and for European detectors, they would be 50, 100, and 150. But that's understood. Then there's this family of lines over here that are to do with the guitar string resonant modes of the fibers from which the mirrors are hanging from optical fiber, from glass fibers as part of their pendulum. So the pendulum is a glass fiber, so it's under a fair amount of tension from the mass of the mirror. And if you twang those are the normal modes of those wires. Now, why do we twang them? The answer is we don't. It's thermally driven. So it's just the thermal noise. And then every other frequency, these higher ones, are calibration lines, and they look really that we inject. Now, they look terrifying to the eye. It turns out they're essentially less than a bin in frequency space when you're doing long, when you look at our long data sets. So they're very easy to remove in the data. So all of the lines are either self-inflicted as calibration lines, or they're lines that we understand but don't remove because they don't bother us.
That is clear to me, but what was not clear is why they are amplified when you are using squeezed light.
Yeah. So I think that's actually also an artifact. I think, for example, if you look at this line, is higher at the black curve. So I think it's just it's the graph, if you will. We are very careful to make sure that squeezing doesn't introduce new noise. In particular, mechanical noise. If there was a new mechanical mode that showed up, that would be due to our squeezer or due to scattering from our squeezer. So we're pretty careful about that.
Thank you. So just on these sensitivity curves, so these instruments are most sensitive in the sort of few hundred hertz range. So from a kind of astrophysics point of view, is that where you want to be, or do you want to go to much lower frequencies or much higher frequencies? Basically, like, where's the sort of interesting directions in here?
Yes and yes and yes. So it depends. So if you wanted to, for example, neutron stars are very interesting objects because unlike black holes, neutron stars have structure. Okay, and so the black holes are only defined by their mass and their spin. They don't really have any physical structure. You don't expect to see bumps or mountains on them. Neutron stars, on the other hand, have structure. And so when the neutron stars get close enough to the edges where we're really starting to merge, you will see tidal disruption of the neutron star. And that tidal disruption will tell you a lot about the equation of state of the neutron star. And so there's a lot of interest to see that, and that happens actually at kilohertz or higher. So they're just lighter and therefore. So we'd love to do better there. On the other hand, if you wanted to see the signatures of either supernovae, or for that matter, supernovae, or if you wanted to track the neutron star when it's still farther out, then you would want to go to lower frequencies. Or if you wanted to see a pulsar, for example, which is a lone neutron star, just rotating on its own axis, those things that we've seen from X-ray observations are usually lower. So really, of the sources that we know, we're driven in both directions. And then there's a bigger question of the sources we don't know about. And so there's this idea of eyes wide open. So you want to be able to look out in every band for the mystery sources that may come up. So, yeah.
Okay, thanks.
So I understand that these glass fibers are isolators, right? Your mirrors are isolating, and you put a lot of light on it, so it's photoelectrons, right? And I would guess that with these tiny forces, that just a few electrons would be enough. How do you make sure that this thing doesn't charge up?
Yeah, so we have UV discharges going on. So not during observation, but we shine UV light to discharge the mirrors periodically.
That is enough. Yeah.
That is enough. Yeah.
Interesting. Okay.
Thanks. Yeah, I had a question about how do you define what the certain measurement is? Like, do you have some theoretician work and that tells you, okay, like this amplitude of this frequency means, okay, these are now 2 neutron stars. And then do you do this observations like automatically, or is there some PhD student who has to go like through all the oscillations?
Yeah, so let me answer both questions. So the way that we make the measurement of the binary system, so the neutron stars or black hole binaries, the Einstein equations give you a pretty good prediction of what the waveform should look like. Now, Einstein equations are actually very difficult to solve. They're quite nonlinear, and we only have exact solutions for very simple systems, like 2 black holes that don't spin. So as soon as you add black holes that have spin, you have to go to numerical relativity. So there's this whole sort of group of scientists, theoreticians, who are working on both the general relativity side of things and the numerical relativity side of things. So and they help populate. They help, and so then how do you look for these signals in this very noisy data is done through match filtering. So it's and so they provide the template of all possible waveforms, and then we do some match filtering to get triggers. Now, once you get there, so first layer is extremely coarse triggering. And so you just look for something with excess power in your match filtering. But then as soon as you get a trigger, then you have to dig deeper. And the complication is that because some of these signals are from neutron stars, which would have an electromagnetic counterpart, you want to do that pretty quickly. Because remember, I told you the optical glow only lasts a few hours to a day. So there's 2 levels of triggers. One is get it out quickly, but with low, with high false alarm rate. And then comes the much deeper analyses of getting to high significance detections and getting parameters. There's a whole nother group of class of science, of course, called parameter estimation. How do you know the parameters of the object you measured? What's its mass? What's its spin? How far is it? What's its inclination angle? And those are done with offline, much more detailed analyses. So there are these online fast triggers, and then offline. And if you ask some poor graduate students sit there and look at it all, it interestingly does, from the online fast triggers are automatic, but then the detailed work is very much involves human intervention.
Okay, thank you.
Yeah, thanks for the great talk. I was wondering if you take any special measures to reduce the intensity noise on your laser sources, and if like the RIN on your laser source is actually limiting the sensitivity in this case.
So the answer is it does not limit the sensitivity, but only because we take huge precautions. So we're operating with a RIN that's close to 10 to the minus 9. And that takes a very significant amount of effort, including some things like non-uniformity of the photodetector on which you make the intensity measurement for your feedback loop. So there's an enormous, actually to get to that RIN level that we operate on has been the subject of maybe 3 or 4 PhD theses, including some that were done here in Germany, in Hanover. But some of the ideas began here. So yeah, very young people in the group may not know, but Garching has an enormous history with gravitational wave detectors. Some of the early resonant mass detectors were here. And then there was a prototype detector that was here. So all through the 80s and 90s, Garching had a very big role in gravitational wave detectors, and then it kind of went elsewhere. And some of those were done here. So is that what it would be? Yes, yeah, so it's 10 to the minus 9, relative. So yes, delta I, exactly, and that takes an enormous amount of finicking. So
thank you. So one question. So what is now then in the end the main limitation for achieving higher squeezing factors? And what do you think is possible in the future?
Yeah, so three things. There are sort of three parts to that answer. The first part is that if we did a lot better with squeezing right now, we believe our thermal noise is right here. So we wouldn't really see much improvement. And for these gravitational wave detectors, it turns out this is called the bucket, the lowest part, and most of your RMS is made up of sensitivity is made up there. So it's really in the bucket that you care the most. But if, as you do better, and we're working on better coatings for, mirror coatings for that, the things that would stop us today from doing better, so we're seeing something close to 6 dB of quantum noise reduction. Our squeezers regularly make 10, 12, 15 dB. We lose a bunch of that to the input optics as optical losses. And when you have these very complex input chains with many optics and large optics and large apertures, controlling the losses is a big challenge. So that's the second thing. And the third part is phase noise. So what does phase noise look like in these systems? Phase noise in these systems look like you have a nice squeezing ellipse, and your phase noise jitters it, and now your signal picks up the long part of your ellipse when it shouldn't. And so those are the three things that we would have to work on to get better. Now, you see these future detector designs, they all assume that we can do 10 dB, some even assume 20. Now, I will say as a practitioner in the field, that is going to require some kind of paradigm shift in optical materials, and but 10 dB I think is within reach, and we make that in our squeezers all the time. We measure that in our tabletop all the time. We just don't get to it in the big detectors.
Thank you.
Thanks.
Okay, one more question.
Yeah, thanks for the very interesting talk. You mentioned this limit on black hole masses of about 100 solar masses. I didn't quite get how this comes along. Could you elaborate a bit on that?
Yeah, so let's see. So what it is so when the way that we believe these black holes, these stellar mass black holes, we're not talking about the supermassive black holes that are in the centers of galaxy. That's another whole mystery. But you look at these stellar mass black holes, one of the things that happens is when a star gets too big, like 50, 60, 100 solar masses, what happens is that it can't, because of pair production. So just the electrons and protons are forming pairs. You can't get to holding the star up, and it implodes. The radiation pressure is enough. You're not forming enough photons, if you will. And so that process is such that it doesn't allow a star to collapse into a black hole. It basically just causes the star to explode. And so there should be no remnant. And so that is the reason why, and we see this in, if you look at the morphology of stars, you see that. And so as a result, there's been this mystery of how do these 100 solar mass black holes form? And the way that you can answer that question is very natural, is to say, well, we see these collisions all the time. Two lighter black holes collided, made a heavier one, two heavier collide, you keep hierarchically building them up. But to do that, then you need some region of space, which we haven't seen, where there's enough density of black holes that these pairs find each other and can do that hierarchically to get all the way to 100 solar masses in the age of the universe. And then there are also possibilities of that. There are these regions in galaxies called globular clusters, which are regions which have much higher density of stars than the average galaxy. So could these be forming in globular clusters? But then when you look inside of globular clusters that we can see with our telescopes, you don't see signatures of very many black holes. So it remains a mystery how the physics will say pair production says you can't form these, and yet they're here. And so then you would say, well, then there must be some other place in the universe where they're being made. Okay. So I think that's a story still to be written.
Okay, more and more questions. If Nergis still has some energy, I'll keep. But I mean, maybe these are the last two now.
Thank you for the fantastic talk. So I have mostly a curiosity. So how long does it take to go from the tabletop experiment to the real implementation? And what does it change from one to the other? Because I imagine the tabletop should be much shorter cavities, obviously. So
So it's a great question, and it's what I've spent my entire career doing. So I'm happy to answer it. So I would say the typical time frame for critical path technologies is 5 to 7 years. And what do I mean by that? So let me give you the example of squeeze. Squeezing is a fantastic example. Remember I said 10 dB, 10 hertz, 10 years? We did it in 6 years. And why? Was it because what happened was that as we were building advanced LIGO, the idea was that we wouldn't really need squeezing till we got to high enough laser power. And then we learned that getting to high laser power was damned hard. Not because you don't know how to make lasers, you didn't know how to control the thermal issues in the interferometer. And at that point, there was a big pivot that said, okay, we're not going to get to the sensitivity just by laser power, and then the squeezing is the alternative, right? And so that was then, fast-tracked. And so you can have such kinds of things, but I would say the typical time scale is of order decade, but usually I would say 5 to 8 years, and some things are just fast track because you put all your resources into it because you need it badly. And then there's another piece to this, by the way, which is that sometimes there are technologies that are ready to put in, but they won't give you any advantage because something else is not working yet, and then you wait because you don't put anything into the big instrument until you absolutely need it, because then your design is locked, right? So.
Great talk. Sorry, but I have a question. From what I know, there's a theory where these big black holes also were created from the join of a lot of black holes, but these black holes were primordial, like they were created in the Big Bang or very. And I have a question. If one of these black holes primordials that have a lot of less mass than a solar black hole explodes because there are Hawking radiation, will the LIGO detect something?
Yeah, so there's a lot of ideas about primordial black holes. So these are very light black holes, subsolar mass black holes that were formed in the very early universe. And so the issue right now for us is, first of all, we don't see any evidence of those. One can look, and one has to look in the low frequency range for that. Okay, these are light objects. But the other issue is that if you think about just sort of the standard inflationary universe, you would expect their signatures to be at high redshift, and we're not sensitive to high redshift. So let me just give you a scale for that. So the 1123, the object that we just put out this week, the most massive black hole pair. So those were 130 solar masses, and we were able to see them out to about 7 gigalight years away. And that you don't even start to write redshift on 7 gigalight years. So we're not at cosmological distances where you can start to really see the signatures of these. So you need more powerful instruments to see the system that the effect that you're talking about. One of these sort of evaporates from Hawking radiation and leaves a poof of gravitational waves. And then there's a third issue there, which is that again, gravitational waves are not emitted because of conservation of energy and momentum. They're not emitted from spherical accelerations. They don't have a monopole or a dipole term. Their lowest moment of a gravitational radiator is quadrupolar. So you also have to have asphericity in the poof when your black hole evaporates.
Thank you.
Okay, I see no further super urgent questions. So I guess it's time to wrap up.
Thank you, everyone.
Thank you very much, Nergis, for this fascinating talk.
Thanks.
And
thank you. Thanks.